Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book, a 3 volume series I wrote from 2019 to 2022. And I'm going through the first 2 volumes, all the lessons in them. I'm up to section 3.2 of the first volume, which is on irrational numbers. And today I'm starting a new subsection on pi. And I'm sure you guys all know about pi, very famous irrational number. Everybody learns it in grade school. Ratio of the circumference to diameter of any circle in a plane. Anyway, let's begin. So, before I start talking about pi, I want to talk about transcendental numbers a little bit because these are a different type of irrational number. So far, I've only talked about what are known as algebraic numbers. There's actually two main types of irrational numbers. They're algebraic numbers. Those are numbers that are roots of polynomials with integer coefficients. And there's another type of algebraic number that aren't. These are called transcendental numbers. And these weren't even discovered until the mid 19th century. I think it was 1851. I think it was Liouville, a very famous English mathematician, who first discovered that transcendental numbers existed. He proved they existed without actually finding any. I think a few years later, he actually did find one. And then, shortly after that, I think around 1882, it was discovered that pi, probably the most well-known irrational number, that one turns out to be transcendental. It's not the root of any polynomial with integer coefficients. So not only is it known to be irrational, it's also known to be transcendental. And it turns out that most irrational numbers are transcendental, kind of in the same sense as most real numbers are irrational. Actually, most real numbers are transcendental, if you want to know the truth. But enough about that. So let's start talking about pi, because like I said, pi is the most famous known transcendental number, and I think you guys all know the definition of pi. It's just the ratio of the circumference to the diameter of any circle. And it's a little bit of a remarkable fact in and of itself that any circle, it doesn't matter how big it is or how small it is, every circle, as long as there's a circle in the plane in Euclidean geometry, it always has the same ratio for the circumference to diameter. In other words, all circles in the plane are similar, meaning they all look the same if you scale them. So this ratio has to be a constant by that fact, and this constant is known as pi, approximately 3.14 if you want to get a little more precise. To 10 decimal places is 3.141592656. Actually, no to 100 decimal places, but I'm not going to rattle out all the digits. I do that in another video. I actually have another video on pi, which I think you guys should watch because it's much more comprehensive than this one. But this just gives you a little taste, and this was what's in my book on pi. So not only turns out, you might wonder why pi is so important, other than the fact that it's the ratio of the circumference of the diameter of a circle. Well, I think that fact in and of itself already makes it a very important number because circles are everywhere. Let's face it, wheels are circles, gears are circles. In engineering, you can't avoid working with circles. And so, because you're working with circles, there are a lot of practical applications where you have to know the ratio of the circumference to the diameter of the circles you're working with. So that's why pi is an important number. That's just one reason. Turns out there's a whole bunch of other reasons too. I mean, pi comes up in a lot of places you might not expect. Not only is it the ratio of the circumference to the diameter of a circle, but it also appears in formulas for the area of a circle. I'm sure you guys all know that the area of a circle is equal to pi r squared, where r is its radius. And it's not obvious that, the formula for the area should involve the same constant as the formula for the circumference, but it does. You can actually prove this using calculus, but I don't get to calculus until volume 2. You don't have to know calculus to know these formulas. And not only is it appear in formulas for the circumference and the area of a circle, but you can go to higher dimensions. You can go to a sphere, which is a three-dimensional analog of a circle. And it turns out that the surface area, both the formulas for the surface area and the volume of a sphere, also involve pi. The formula for the surface area of a sphere is 4 pi r squared, and the formula for the volume is 4/3 pi r cubed. So pretty remarkable that all these formulas involve pi, and you can even extend this to higher dimensions. I don't talk about this in my book, but it's possible, even though we live in 3 dimensions, it's possible to mathematically describe higher dimensions. As a matter of fact, any number of dimensions you want. And you can define the analog of circles and spheres in any dimension you want. And you can talk about the analogs of the surface area and the volume. They're not called that. I think they're called content or something. But the analogous formulas all involve pi. Turns out they involve powers of pi, but they still involve pi. So pretty remarkable that all these formulas involve pi. And pi appears in a lot of places you might not expect. Some applications for pi don't even seem to involve circles at all. Like when you struck up the normal distribution, for instance, that involves the square root of pi of all things. You might wonder how the square root of pi appears in mathematical formulas, but it does. And not only mathematical formulas, but physics. There are a lot of very, very, very important theories in physics where the formulas involve pi, including Maxwell's equations of electricity and magnetism, as well as the field equations for general relativity. I'm not going to get into that here. But pi appears all over the place. It's a very, very important number. I think most people still consider it the most important irrational number. I guess a close second is E, but I don't get to E until volume 2. E involves calculus. In case you're interested, E is approximately 2.718. Very important number, but I'm not talking about that yet. Another transcendental number, by the way. And E was known to be transcendental before pi. E used to be called the base of natural logarithms. Now it's called Euler's constant. E for Euler. Anyway, enough of that. And the last thing I'm going to talk about today, I also do this in my book. Pi has been calculated to just amazing precision. I mean, it's known that it never ends. It's known that it's for one thing, it's irrational, which means that the decimal expansion never terminates and it doesn't even repeat. But not only that, like I said, it's transcendental. But the accuracy to which people have known pi throughout history has grown just amazingly. I mean, I think I mentioned in a previous video that it was the ancient Greek mathematician Archimedes who gave the first accurate estimate of pi. He got it to about 3 decimal places, basically between 3 and 1071st and 3/1/7, approximately 3.142. That was back around 250 BC. And then if you look at this graph on the bottom, this just shows you the history of how accurately pi's been known. And even before computers, it was known really accurately. There was a English mathematician, I think his name was Shanks, who in the mid to late 19th century, I think he spent 20 years calculating by hand 700 digits of pi. Turned out he made a mistake on the 527th place. But he got 527 decimal digits of pi correct before computers. Pretty amazing. And then I think it was 1946 that ENIAC made the first calculation of pi to 2,000 decimal places. That's when they, so it was almost 100, like 70, 80 years that Shanks' estimate of pi kind of, held. But then it wasn't until that was computed with the first computer on ENIAC, and they determined that only the first 527 digits were correct. But then they need 2,000 digits. Today, there's like over 100 trillion digits of pi known. I mean, that's just a mind-boggling number of digits. Think about it. I mean, on a typical book, you can only print about 1,000,000 digits. So we're talking 100 million books. It would take 100 million books. I think that's bigger than any library in the world. I think it's even bigger than the Library of Congress. I don't think the Library of Congress could hold all the digits of pi in books. But of course, we have computers now, and now we have big databases. We can hold all this information. Another really interesting thing about pi, I mean, we have such accurate formulas for calculating pi. Of course, we have computers, but not only that, we have formulas that converge just amazingly fast. I mean, I think the fastest known converging series for pi, each term adds about 15 decimal places. I even read this. I couldn't believe this when I first read this, but about 20 years ago, I read that the algorithms that are used now to compute pi are so fast that it takes just a little bit longer than the same amount of time it would take to add two numbers with the same number of digits. So think about that. We know 100 trillion digits of pi. You might wonder how the hell we know so many. Well, it turns out that the computing power to compute that many digits of pi is about the same computing power as you would need to add 200 trillion digit numbers. Pretty amazing. I mean, you might wonder, why do we need to know so many digits? I mean, there's not much practical need. And I talk about this in my video on pi too. If you're talking about purely practical applications of pi, like in math and science, then there's really no need to know them more than about 40 digits of pi. Because if you knew 40 digits of pi, you would be able to compute the circumference of the observable universe to the precision of about one atom. When there's no practical need to know any better than that. So just we're already 40 digits is kind of the practical limit of what you might care about. But there are other reasons for wanting to know more. I think the most practical reason for wanting to know a lot of digits of pi is because it's a good way to test software. I mean, there's only one value of pi. So if you write if you're if you have a new computer system and you have some software, some hardware, and you want to make sure that it's calculating everything correctly, a good thing to do is to have it calculate a lot of digits of pi because we already know the value. And if it calculates the right value, we know we can be pretty sure it's working. That's probably the most practical reason for knowing a huge number of digits. There's also a lot of curiosity. I mean, one good answer I've heard a lot. It's kind of like climbing Mount Everest. We do it because it's there. It's a challenge, right? And we like a challenge, kind of like how we went to the moon. I mean, I don't think there was much practical reason for going to the moon in 1969 other than trying to beat the Russians into space. But, we did it because it was there and it was a big accomplishment, exploring a new frontier. And if you can think of math as a new frontier, so you can think of, computing a huge number of digits of pi as exploring a new mathematical frontier. I think that's a good enough reason in and of itself. But there's other reasons too. I mean, for a long time, people were wondering if there were any kind of patterns in the digits of pi. They thought maybe they could see some. They didn't repeat, but they thought maybe it has some. Kind of interesting patterns. Like there's numbers called chaperone nouns constant. The digits are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so on. It doesn't repeat, but it has an obvious pattern. I think for a long time people thought maybe pi has a pattern to it. There's even a famous science fiction novel by Carl Sagan called Contact. And in the book Contact, they didn't put this in the movie, but Ellie Arroway, the one played by Jodie Foster in the movie, she actually calculates pi to some huge number of digits, and she does find a pattern on it. And that's kind of proof that according to the story, it was the aliens who actually were able to alter the value of pi. I don't know how they did it, but they encoded a message in the digits of pi. You'd have to read the book. It is science fiction, but I don't think there's any patterns in the digits of pi, but you never know. I mean, pi is what's called, people believe that pi is what's called a normal number, which means that basically there's no pattern in its digits. Its digits are as random as they can be, as random as anybody can, as random as you expect if they were random decimal digits. And not only is it assumed to be normal in base 10, but normal in every base. And as far as anybody's done any tests on the digits of pi, that seems to be true. Doesn't seem to have any pattern in its digits. Not only no pattern in its digits, but no pattern in its continued fraction coefficients. I'm not going to go what that is right now. I do talk about continued fractions later. I think in another week or two I'll mention them. But Pi doesn't seem to have any special structure, but it's there and it's interesting. And anyway, that concludes my video on pi. So thank you for watching. Long live math, and I'll see you guys next time. Bye.